Okay. So reasoning shortcuts. So this was something I came across in preparing one of the other lectures, and it's super interesting. So, okay, so we have everyone, I think, is sort of familiar with examples like machine learning fails when, a bunch of wolves, a bunch of dogs, like the dog in the snow, and the right? We've all seen it. It's obvious, you see an animal, whatever, learn a bunch of features of snow, and the thing that, could be a dog or a wolf, continue to say it's a wolf because all your training data is wolf in the snow. And of course, there's like all these things like aliens maps, and to get idea for what evidence animal is a husky animal is being blue. And aliens map is kind of showing the same thing. Sometimes these techniques, show you the difference. Sometimes you get results like this, and there's really, no assurance of what happens, if it's going to actually work. So, okay, so we see all these kind of normal complaints about machine learning, and of course, AI to the rescue, right? But, big problem is Neuro Symbolic combining the best of both worlds, gradient learning plus logical structure. We got all these great methods, right? Well, it turns out that you can still have some serious mistakes. So let's just review a quick setup, and I'm going to use this setup in this lecture. You'll see it's very similar to a bunch of the previous lectures. We have some logical knowledge base, K, and we say that we have some function, K, is a measure of the inconsistency in the knowledge base. And then we have training data, X is our vectors, Y's our ground truth labels, and here's our data set of the XY pairs, that's the training data. And we have a set of primitives or concepts, and they are in the language of K. And we have some perceptual model that maps features to concepts. So P beta X returns a concept or set of concepts for sample X. And so using gradient descent, we want to minimize the following. The knowledge base, the ground truth, dealing with the results of the perceptual model, right? Because if some of the concepts in the perceptual model combined with K, for each sample, it should give you the label of sample I and not something wrong. But that's all stuff you all should be sort of familiar with. Right? Okay. Here's the thing. One of the things about gradient descent is one of the reasons that a lot of people think it works as well as it does with neural networks is that through overparameterization, there's actually a whole bunch of solutions that it can reach that will be optimal in terms of that model. And so you don't have a unique solution. So what if we have perceptual failures that make it easier for the logic to work? So we confuse two different things. If we confuse all dogs with wolves, for example, and all we care about is something at a higher level concept, maybe the system can get away with that. So what you have is you have functioning logic, minimize loss, but the reasoning behind it is all screwed up because I defined everything wrong. So it's like raising a little kid and telling them that everything that's green is purple and letting them believe that their whole life. So This misinterpretation of symbols is called unintended semantics, and it leads to what are called reasoning shortcuts. So it's finding this sort of shortcut through the optimization process. It's like, aha, that's optimizing the loss function, so that's the right semantics. I'm just going to go with that with the shortcut. So quoting right from the paper, simply predicting multiple concepts jointly from a single neural network is sufficient to enable reasoning shortcuts intuitively because the network has access to both properties of objects. It can automatically exploit correlation to satisfy the knowledge. That's kind of the key thing. It's going to exploit these correlations to satisfy the rest of the knowledge base. And that's what gives rise to these unintended semantics. So how to think about this? The authors of this paper came up with this sort of theoretical model of how things are generated. So let's say we have two factors. We have some ground truth, what the objects really are, and some stylistic variation. So of course, you know, this could be variations due to the sensor use, or if it's handwriting, how the digits are written, or whatever. And both the ground truth and style items contribute to text that's actually perceived. Yeah. However, only the ground truth is associated with the actual label. And of course, this is assuming we're going to generally make the assumption that there's no issues with the logic program. Okay. So, going from X to C, this is where the perceptual part of the neurosymbolic system comes into play. And the neurosymbolic system then uses C to deduce Y to Z. So the goal of such a system is to have a correct understanding of the underlying semantics and allow it to infer the target label. So essentially, we have this perceptual model. We want it to be equivalent to providing the equivalent probability distribution to the ground truth labels of concepts. So G is the ground truth of the concept, both conditioned on X. That would be the goal. So what happens with the reasoning shortcut is you get some P theta that is not equivalent to this P star. So, okay, so we have, you know, if you look at your loss function, you have your loss function, you're looking to find the parameters that over the data points are minimizing or maximizing that function, depending on how it's framed, based on both the data and the knowledge base. And you have a reasoning shortcut when you do that, and the P theta is not the same as P star. So the strategy to reduce these is first, can we just see if we can somehow count the reasoning shortcuts? So we know there's got to be at least one valid path. If there's a valid solution to the problem, P theta equals P star, and you're good to go. Okay, but of course, finding a unique solution is going to be very difficult. So what we want to do is analyze a bound on how many of those are there. We can then develop a strategy to just reduce the number and employ those strategies as part of our approach. And then here we'll show the author's results from empirical evaluation. So they introduce this notion of a function alpha, where they say, okay, we're going to say for some deterministic model P theta, there is an associated alpha function where you're mapping that maps the ground truth concepts to C. Okay. Now in P star, this is alpha of some C is going to equal C. It's going to be different than anything else. And so here we're just looking at this alpha function and counting how many of them can exist. So first is they say, okay, we're going to have a theorem to put a bound on the number of these threads. Or this is actually a full count because you actually have alpha. And you're just going to say that, well, I have a little walkthrough here. So they introduce this function beta of k. It maps concepts to target labels based on k. And then you have this composition bk composed with alpha, and that maps predicted concepts to the target labels based on k. And so essentially all we care about here, both these functions are returning the ground truth concepts, the y. This is mapping the concepts to there, and this is mapping the predicted concepts to the final. When they're equivalent, we're going to conclude in our count. Regardless of the concepts are the same. The concepts are the same, that means you have a correct solution. If it's different, it's the reason for it. But and the general idea is you're going to only have one good solution with semantics of I. And you have a whole bunch of these other functions where you have a different alpha that's incorrect. Now, one thing to note here is this may sound really difficult because you only have one alpha that's going to be right. But this doesn't mean for the result of gradient descent that there's only one solution you could have, because there could be multiple assignments of weights that can lead to the ground truth solution. Also, this particular result is for the deterministic case, which is also a simplification. They do include another theorem that builds on the non-deterministic case based off of this. But I'm just going to keep talking about the deterministic case to keep it simple. The results, the relationship between direct, so it's not that big of a deal. You reduce one, you reduce the other. Okay, so the key here is when you look at this quantity, it's related to the number of satisfying assignments of what's being counted in here. This is a conjunction over all these potential ground truths. Okay, so if we can reduce the satisfying assignment, we'll reduce the number of reasoning shortcuts associated with it. Now, one way you could do this is you could make this conjunction longer. For any logical conjunction, I say, hey, what are the number of things that satisfy A and B? Well, what if that's going to be much greater than if I say it satisfies A, B, C, D, E, and F? Or you could think of it as almost like a database, right? Give me all students in CSE 598. Give me all students in CSE 598 that are in their second year of their master's program. All students in CSE 598, second year of their master's program who are applying for a job in Silicon Valley. It gets less and less the more constraints you put on. We're taking the same strategy here. Associated with that is also the size of the knowledge base. That also constrains the problem in a little different way. You have larger knowledge base, you have more constraints there. You also reduce the Okay, so the first is with multitask work. And the idea is that if you have a set of concepts and they're used for multiple tasks, then that effectively functions as additional constraints. And you see what happens here. You now have the conjunction on the inside of the first one that is over T tasks. So you could think of it as, so if I tell you, give me all pairs of real numbers, let's say all pairs of natural numbers between 1 and 100 that sum to 20. But then I say, okay, give me all natural numbers between 1 and 100 that sum to 20, and numbers such that their sum or such that their difference is 5. Okay, so right away, because you have the extra task on, you reduce this. You could also think of it, going back to the driving example, maybe we have a task dealing with safety, maybe you have a different task dealing with, recognizing it as destination. Two different things, but they may have to have a lot of the same underlying concepts, such as the lines on the road, the traffic signs, where the parking spaces are, and so on. Those concepts would maybe deal both with the two different tasks. Now, of course, the downside to this is you might not have an additional task. So that would kind of, not be good. And also, identifying additional tasks and doing that extra work may also end up, leading to computational issues as well. So here's some results on doing this. So they look at evidence problems. They look at learning, add and multiply digits, and then so when they evaluated this with 3 different neurosymbolic frameworks, problem semantic loss, which is the competitor to SPL from the other day, and of course, logic networks. And you see what happens, how these perform individually. Why is ground truth the concept? So if you look at the ground truth, the big semantic loss, on the ground truth, it's doing really well. But we see clear reasoning shortcuts. That's got failure from the addition problem. And it's only getting 76%, which sounds okay, but that's down from 100% on the ground truth. But when you have both tasks together, it's doing quite well. And we see this across the board in this example. So that's I think a nice intuition that is validated here. So we can also see here, looking at confusion matrix, what happens when you have add only and multiplication only. You see, almost all the time, you don't have any diagonal lines. So you see it's quickly becoming confused. But when they're combined together, everything's looking all right. 2 different mathematical operations, and it allows us to sort out some of the details between the digits. And again, remember here, this problem was not supervised on the digits, only supervised on the Bible. So the digits are the concepts. Okay, so next, speaking of supervision of the concepts, why not just supervise the concept? We have the data. So this, of course, has, it's obviously going to help things. It's essentially adding an additional conjunction. And this idea already, we've seen it in some of the other papers we looked at. We've seen ABL does this to bootstrap things. They use some initial supervision of the primitive. And LPM does this all the time. The downside is you might not always have that data. And here's the ground truth concepts. So one thing that could be considered is maybe having some unsupervised approach to sort of separate out the concepts. So I want to learn not that they're sort of far away from each other in the future space. And this becomes helpful when you, when the unsupervised model is not separating things based on stylistic properties. So if we had an unsupervised, you're doing this with eminence, and the unsupervised model was separating out people who write, very block letters from cursive, that's not going to be any good. Whereas separating out by digits, and if you remember from earlier in the term Satnut paper, Forpan is essentially doing this with their unsupervised step for Satnut. Another approach is just heuristic approach. So the authors are not able to prove any kind of reduction in the number of reasonable shortcuts using entropy. They do note it may not be appropriate in certain domains because you may not want to, minimize necessarily the diversity of the result in all cases. However, in the problems they look at, it does have an impact. So here we have H is entropy, C is supervision on concept, and R is reconstruction, which is unsupervised. Unsupervised control over the concepts. So again, here we see the math. Generally, steady increase, the more you pile on together. More on the concept. So that's also kind of the neat thing about it. These things are all reducing the reasoning shortcuts in different ways. So here's just an example of, again, the confusion matrix, what happens and this even odd thing. And you see with deep crop log and LPM, when you're running all the different methods together, they go from being sort of very poor confusing matrix on the concept to being diagonal blind. Interesting to see that these results aren't uniform across all methods. Another idea is what they call architecture-based, where you can factorize the perceptual function. And this also causes alpha to factorize in turn, which reduces the number of mappings. And so they also show here highly effective in reducing your reasoning shortcuts, providing really good results compared to the baseline, effectively eliminating all reasoning shortcuts. However, in order to factorize it, you have to have some knowledge about the underlying problem in order to do so. And here again is the confusion matrix. This one got perfect results, no surprise there. And it got those results across all three neurosymbolic methods. So, machine learning can provide correct answers for the wrong reason, but neurosymbolic methods can too. I think that's kind of a big important lesson. But, mitigation, either making some assumption, adding more constraints, adding somewhat supervision to part of the problem, can go a long way in reducing shortcuts. And what's nice about this paper is, now we're getting to the point in neurosymbolic reasoning where people can start to look at, hey, what are some common approaches? Are they in fact